Hello everyone, in this video this is gonna be a short lesson, okay, and we're gonna touch on something called the tangent line approximation. So I realized I didn't do this lesson, and it is a pretty important one, so I'll quickly do it. Okay, and the reason why it's not super long is because it's very intuitive. Okay, so let's say you had the tangent line. Okay, you were drawing the tangent line at a point. This is our tangent line. So our function is f, and this is our point. Let's make this our point, okay? This is x, comma, f of x. Now, what the tangent line approximation says that if you have a tangent line at a point x, you can approximate another value, is called that b. So let's say we had b, and that's close to x, okay? This is quite close to x, okay? So you can, if this line is, let's say g, okay, g, so g of x is tangent to f, then if b is close to x, so b is approximately equal to x, then g of b equals f of b. Not equals, but is a good approximation for f of b. Okay, so if you were to zoom this in, okay, if you were to zoom right in, it's our tangent line, then if this is our b and this is g of b, this is f of b, and it's only slightly different. It's only very slightly different. And you could see this in action if we do some practice. So usually on the AP exam, they might ask you for a tangent line approximation. Okay, and this is exactly what they mean. You find the tangent line, okay, preferably at the point they give you, okay, and you approximate a value close to it, okay, approximate a value of the function that they ask for. So let's say this is 1, 1, okay, this is 1, 1. So the tangent line at that point is this, okay? And what is this tangent line? Okay, we're going to use this tangent line to approximate. So if f of x equals x squared, what is f of 1/2? Okay, so what's an approximation for f of 1/2? Okay, so f of 1/2 you can easily calculate to be 1/4, or 0.25. However, we're going to use our tangent line approximation. So what is our equation of the tangent line? Well, the derivative f prime of x is equal to 2x. That is equal to 2x. So the derivative at x equals 1 equals 2. So with our slope at x equals 1, we can just use the point slope form. Equals 2 times x minus 1. So we get y equals 2x minus 1 if we were to solve for y. So this is y equals 2x minus 1. So if we were to plug in 1/2, you get 2 times 1/2 minus 1, which equals 0. So f of 1/2 is approximately equal to 0. And you can see that's not really a great approximation. I mean, it's good in that it's only 0.25 off. It's only a quarter of the way off. However, it's not really that reliable if you want to be really precise. However, as you get closer and closer to 1, x equals 1, look, watch what happens. Okay? Watch what happens. Then the tangent line and the actual function become closer and closer and closer until at x equals 1, they align for an instant. So if we were to approximate f of 0.999, well, if we place it into our function, okay, and we're going to use a calculator for this, okay, you get 2 times 0.999 minus 1. And we get our approximation is about 0.998. What is 0.999 squared? Okay, so the actual value is 0.998001. So now you could see, if as you get closer and closer to 1, the approximation becomes really, really accurate. Okay, we were 1/1,000,000th off. Okay, 1/1,000,000th off. Okay, so we were not even 1,000th of a decimal off. We were 1/1,000,000th. Okay, it's accurate to 1,000,000. It's accurate. Okay, it's very accurate. Okay, and you could see that as you get closer and closer to x equals 1, it gets more and more accurate. And this leads to another topic known as a differential. Okay, since it extends from a differential. So let's say we had our function. And we had a tangent line at, let's see here. So I'm going to draw a tangent line. Best I can draw it. Let's draw something a little more believable, shall we? Let's try. Okay, that's good enough. So this is our tangent line. Okay? So if this is x, okay, this is our graph f. And now what we're going to do when we do differentials is basically use the tangent line approximation, okay, and approximate changes in x and y. So let's say you had another point, okay? So you had another point B, okay? And this distance is delta x. To change in x, that's what delta means. What is change in y? Okay, you see that the change in y, okay, the change in the y coordinates, if I were to extend these out, you get the change in y is this. Okay, this is f of x, this is f of b. Now, what happens if I approximate using the tangent line? So delta x, or usually given delta x, but change in y is, the change in y we get by the tangent line approximation is not that accurate, okay? So you can't really use a tangent line for big distances. But what happens if we get b very, very close? Okay, let's say about here. Okay, so b comes over here. Now this is delta x. And because the tangent line approximation gets better and better and better as you get closer to x, the point of tangency, then our approximation for the change in y becomes better and better and better. Because look, the distance between the tangent line and the actual function starts to approach 0. Okay, so it gets closer and closer to aligning. Okay, approaches 0. So as x, delta x becomes smaller and smaller, it reaches an almost infinitely small size. And that's what we call the differential of x. It's a notation. So differentials of infinitely small quantity. Okay, it's an infinitely small change. It's like delta x, but super duper small. Okay, and just based on the tangent line approximation, a change in y, okay, the differential of y, this tiny change in y, okay, is, you can approximate it, is equal to f prime of x, where x is our given value, times dx. Okay, and you can kind of see where all this notation comes from. Okay, just more. Okay, so this is what the differential of y is defined as. This is how the differentials relate to each other. Okay? Because the dy predicted by the tangent line approximation, okay, you can relate it through the slope. Okay, so if we had the tangent line approximation, it's our point of tangency, not really a straight line, but okay. If this is dx, this is dy. Okay, dx is our super small change. This is dy. And this equals f prime of x, because f prime of x, as you remember, is our slope. Okay, so we have a change in y over change in x. Okay, must equal f prime of x. That must equal our slope. So dy dx equals f prime of x. Sort of intuitive by now, so notation. So because these are both quantities that we're representing, you can multiply by dx. You can't really do that when you're talking about derivatives, but it's intuitive to think of it that way. Okay, because these are quantities, you can get this relationship. Okay, you can get this relationship. So differentials are basically very small changes, and you can approximate changes in y and x as you get using the tangent line approximation as you get closer and closer and closer to your given point. Thanks for watching. If you have any questions, please comment below and like this video.